We said before that when we try to find the number of permutations we can make with a set of objects, we have to consider position. We think permutations or position. But when we talk about combinations, that position no longer matters. So we start here with this table that we built before, where we looked at these two formulas for permutations. Now we want to look at the repeats and no repeats situation for combinations. Remember, permutations is order matters, think position. Combinations is order does not matter. Now, the easier formula to start with for combinations is the no repeats formula. Let's look back at the example we were using before of the 3 playing cards, where we started with the king, the queen, and the jack. We said that in the no repeat situation for permutations, let's say that we're starting with this set of 3 cards and we want the number of permutations when we choose 2 of these cards. Well, that's the situation where n is equal to 3 and k is equal to 2. And in this formula for permutations with no repeats, we said that we ended up with 3 factorial divided by quantity 3 minus 2 factorial, which was equal to 3 factorial divided by 1 factorial, or 6 divided by 1, which was 6. And that makes sense because if we choose 2 of these 3 cards, we can either choose the king and the queen, or we could choose the king and the jack, or we could choose the queen and the jack. These are the only 3 combinations of 2 cards that we can pick from this group. So we have 3 possible arrangements here, but when we're thinking about permutations, remember that the order matters. So within each one of these, we have to consider the order in which we could pull these cards. With this set of 2 here, we could either pull king then queen, or the opposite, we could pull the king second with the queen first. So we can arrange this set 2 different ways. Same thing over here with the queen and the jack. We could arrange queen jack, or we could arrange jack queen. And same thing over here, either king jack and then jack king. And so we end up with 6 different arrangements if we're starting with a set of 3 and choosing 2 and the order matters. And that's why we end up with 6 permutations. Now, as you can imagine, what happens here with combinations and no repeats is that we're looking at the exact same thing as we did here, except that order doesn't matter, which means that this whole second row here would disappear. In the combination row, king-queen is the same as queen-king, king-jack is the same as jack-king, etc. So the order doesn't matter, it's just the number of combinations, just the different distinct sets of 2 or pairs of 2 that we can pull from this set of 3. And so what this formula ends up being over here for combinations with no repeats is actually exactly the same as this formula, permutations with no repeats. We still have n factorial in the numerator, and in the denominator, we still have quantity n minus k factorial, like this, n minus k factorial, but we just divide by k factorial. And that would make sense here because we're choosing 2 items. And so if we take this permutations formula, this is the set of all the permutations, notice here how we just divided this by 2. We took away half of the items, we divided by 2, which means we divided by k factorial because k is 2 and 2 factorial is 2. And this formula holds up for any n choose k that we pick. This formula specifically, this combinations with no repeats formula, is so important. We use it so often that we give it a special name. We call it the binomial coefficient. And you'll see it written many ways. You'll often see n choose k, the combinations we can make from n items when we choose k of them. Sometimes you'll see it as c and then nk like this, which means the same thing. We also write the binomial coefficient this way, in parentheses with the n on the top, the k on the bottom, and this means n choose k. It's the combination made from n items when we pick k of them. And all of this notation is referring to the same combinations, no repeats binomial coefficient formula. This is also the formula that lotteries often use. For instance, it's often common in a lottery for them to choose 6 numbers of the numbers 1 through 49. So if you think about the numbers 1 through 49, 1, 2, 3, etc., all the way up to 49. And the lottery is going to draw 6 of those numbers with repeats not allowed. And the idea, of course, is that if your lottery ticket matches all 6 of the numbers drawn, then you win the big jackpot. But if we use this formula to calculate the number of combinations that are possible when the lottery can pick any numbers between 1 and 49, of course, we could plug in here and find that the number of combinations is 49 factorial divided by, if we're choosing 6 numbers, which we often do, we would say 6 factorial and then 49 minus 6 factorial. This value here, of course, simplifying to just 43 factorial, which means that we could rewrite this as 49 times 48 all the way down to 44, at which point the 43 factorial will cancel out the rest of the factorial in the numerator. So we have 49 all the way down to 44, the product of those integers, and then we have 6 factorial in the denominator. And if we use a calculator to do the math here, what we find is that this comes out to a little bit over 13.5 million, even 13.6 million, which means that if you're playing a lottery ticket trying to match exactly 6 numbers, you have a 1 in about 13.6, a little more, 13.6 million chance of matching exactly those 6 numbers. So that's the idea here with this lower right-hand corner. And then the last idea is combinations when we can repeat values. This one's probably the hardest to understand, but the easiest way to visualize it is to think about an example. So let's say, for instance, we'll set up a table here. Let's say, for instance, that we are an online health food store. And as we're shipping products out to customers, they order from us, we pack their order, we ship it out to them. And before we send out the box, we want to include 3 little small samples of other products in every shipment so that we encourage customers to try new products. For instance, maybe we throw in a little sample protein powder, hoping that they will try that protein powder, like it, and then order a full-size product from us in the future. So let's say that in all the shipments going out this month, we have 8 different samples that we're including. So A through H here represents sample A, sample B, sample C. Maybe A is the protein powder, B is a piece of chocolate, maybe sample C is a small bag of healthier candies. So we have these 8 different samples here. And all we want to do is include 3 samples. And let's say we're allowing for repeats. We just want to grab 3 samples from our 8 different bins here and toss 3 little samples into each box going out to customers. What we want to visualize then is that we have these 8 different bins here. If you can imagine 8 bins full of these little sample size products, and all we want to do is grab 3. So for instance, that means that we could grab, let's say, 2 of sample A and 1 of sample D. We could also do 1 of sample C, 1 of sample E, and 1 of sample F, or we could do F, F, and G. And of course, many, many other combinations when we're allowing for repeats. These are just examples. The idea here is that we always have to choose exactly where we're putting each of our 3 X's in this diagram. Once we know where we're putting each of the 3 X's, then the rest is sort of determined for us. In other words, at a basic level, once we know we're choosing 2 A's and a D, we know that we don't have anything in B, C, E, F, G, or H. And so if you think then about sort of dividers between these buckets, so if we imagine dividers between each sample bucket like this, we have 7 dividers because we have 8 different sample types. We could really almost say that we're choosing 10 things. For instance, with this first row here, if we have 10 spots, we're saying that we're choosing 2 of sample A. So we're putting an X here and an X here. Then we're putting 3 dividers. So we're saying then we have 3 dividers until we get to D. We're putting another X once we arrive at D. And then we have 4 more dividers, 1, 2, 3, 4. That's the first example. In this second example, if we look at the dividers here between each bin like this, we're saying that the arrangement we're choosing here, if we put it below these lines here, is divider, divider for these first two, and then we're choosing a sample from C, and then two more dividers, and then a sample from E, and then another divider, and then a sample from F, and then two more dividers. That is our choice. That is our arrangement in this second example here. So you can kind of get an idea that what this really comes down to is a choice of 10 spots, of how to fill 10 spots. We need 3 sample spots. We're choosing 3 X's. We're positioning 3 X's. And then the 7 dividers that came from the divisions between the 8 samples, we fill in the rest of the choices with those 7 dividers. And so instead of this idea of the binomial coefficient n choose k, like we said down here, n choose k, where we're picking from n things and we're choosing k of them, this time we're picking from, we'll set up sort of an analogy to our binomial coefficient here, we're picking from n plus k minus 1, because here we had 8 samples, so we had n equal to 8, but we have to position the 7 dividers. There's always one fewer divider than the number here of buckets that we're dealing with. So the number of dividers we have is always n minus 1, and the number of x's that we're placing is k. So we're adding together n minus 1 and k, so you can think about this as n minus 1 plus k, or we write it as n plus k minus 1. So we're picking from a set of n plus k minus 1, or in other words, just replacing in this formula n with n plus k minus 1 when we're still choosing k objects. So in this notation, it looks like n plus k minus 1 choose k. And in our formula here, instead of n factorial, we have n plus k minus 1 factorial. And in the denominator, we'll still have k factorial here, but we're replacing n with n plus k minus 1. So we have here, instead of n minus k, we'll replace this n with n plus k minus 1. So we get n plus k minus 1 instead of n right here. And then we still have minus k, so minus k. Well, when we do that, we get this positive and negative k to cancel, leaving us with just n minus 1, which means that we get n minus 1 factorial here in the denominator. So this formula is exactly the same as this one. We're just replacing n with n plus k minus 1, and we see that logic based on this bucket divider illustration, where we realize, like in this example, that we had to fill 10 spots. We had to fill n plus k minus 1 spots with k choices. We pick where our k items are going to go. We have k number of x's and we position those, and then we fill in the rest with dividers. So in this example here with our online health food marketplace, if we're choosing k equals 3 items out of our 8 samples and we're allowing repeats, then we have 8 plus 3 is 11, minus 1 is 10. There's our 10 buckets we have to fill. So in the numerator here, we end up with 10 factorial. Let's put that up here. We get 10 factorial. In the denominator, we have n equals 8, n minus 1 is 7, so 7 factorial, and we said that we're choosing 3, so we have 3 factorial times 7 factorial, 3 factorial times 7 factorial. Well, we know that this 7 factorial will cancel with the 7 factorial that's nested inside this 10 factorial, leaving us with just 10 times 9 times 8 in the numerator. And so when we do that math, 10 times 9 times 8 is 720 divided by 6, because 3 factorial is 6. The result there is 120 combinations. So if we have 8 different samples we can pick from, we're picking 3 of them, and we're allowing repeats, we have 120 combinations that we can create in that scenario. So even though combinatorics is the study of counting, hopefully looking further into factorials and permutations and combinations gives you a much better idea of why these counting concepts are so valuable to us and why these come in handy for so many different real-world applications.